The photon hypothesis from Einstein was meant as a solution for the behavior seen in the photoelectric effect. Einstein is the first person who can really think of who thought of electromagnetic radiation as a discrete particle. In Einstein's view, photons were particles with energy E, which is equal to Planck's constant times frequency. He introduced the idea of light hitting the metal, but not acting as a wave, but rather as a particle, the photon. In his model, this was somewhat of a hybrid, because the photon carried an energy E which is equal to h times f. F in this case is the ordinarily thought of frequency of the traveling electromagnetic wave. So he was using wave words at the same time as he was talking about a particle, the photon. Einstein knew that the photon was massless because in his theory of special relativity, light travels with the speed v equals c. And in relativity, we know that that means it has to be massless because the speed beta of a particle is equal to pc over e. And if it's supposed to be 1, because this is a velocity is c photon, how's that possible? Well, pc is just pc, but e is the square root of pc squared plus mc squared squared. For that to be 1, that requires that the mass m is 0 for a photon. This also means that pc is equal to h times the frequency, or written a different way, p is hf over c, or p is h over lambda. That last formula uses the fact that v is the velocity of a wave is lambda times frequency, and v is equal to c for light. That formula p is equal to h over lambda is something we're also going to see again when we start talking about matter waves as well. But here we've derived it for photons. So how did Einstein's theory of the photon and its energy packet account for the photoelectric effect? Well, he suggested that the electrons that were in this metal, in this case a sodium metal, were actually buried in a potential well of height W, which he called the work function. That's the amount of energy it would take to pull an electron out of that metal. So you can picture it as a little one-dimensional potential here, where V of x is equal to 0 whenever you're outside the metal, and V of x is equal to minus W when you're inside the metal. So the electrons sit in the metal, they have a potential energy that's negative. They're buried in there. We're going to imagine that the photon is a packet of energy that comes in and is absorbed by one of the electrons, like so. When that happens, the electron now has more energy than it used to, and it's going to acquire some kinetic energy. In other words, it's going to take all the energy given to it by the photon. Of course, it won't get it all in terms of kinetic energy because it's going to have to subtract off the potential energy to climb out of that little well right there. So it's going to skirt off to the side. The equation we would write then is the kinetic energy of that electron after it leaves the metal is going to equal the energy given to it from the photon, which is h times f, minus the amount of penalty it takes to get out of the metal itself, which is W. Later, when experimenters like von Leonard and others start measuring the kinetic energies of the electrons, they're doing that using this thing called the stopping voltage. They're, in other words, taking that kinetic energy and converting it into potential energy by making the electrons stop in midair because of the electric field applied to across a plate. So they're not measuring kinetic energy directly, they're measuring voltage that makes the electron current stop in an apparatus like von Leonard's. So what they measure is frequency of light injected into that metal, and they measure the resulting stopping voltage that makes the current stop in their apparatus. This is the formula that was derived by Einstein and in perfect agreement with the experimenter's observations about the photoelectric effect. Voltage rises linearly with frequency, has nothing to do with intensity.